Okay, the streaming has started. I will just paste the link in the chat box here. Okay, so you can come back later and watch the recording in the YouTube. Let me also share my screen. So in the last session, we have discussed uh, the importance of parameter estimation and what are the key metrics that we test for a good estimator. And then we talked about bias, variance, and risk of an estimator. And we also talked about the two approaches that we can come up with an estimator, like two methods that can help us getting a good estimator. One is method of moments estimator and the other one is maximum likelihood estimator. And today we will see the third method, which is Bayesian approach, where the key difference between the method of moments and maximum likelihood with the Bayesian is in method of moments or in maximum likelihood estimate, we treated our parameter to be a constant. But in Bayesian,
The
what
screen is
Bayesian
not
does,
visible.
yes, I just shared my screen, it will come. I hope the screen is visible, right?
Yes, sir.
Ah,
Yes, sir.
so in the last class, we discussed all these things with an examples. Now let's continue the discussion from here. Okay,
Sir,
so
can you share his notes?
yes. After this session, I will share the complete notes.
Or is there recording of the previous class, sir?
It's available on YouTube.
Okay, thank you.
Yes. So yeah, the next method which we are going to look at is the Bayesian method, where in this method we treat our parameter to be a random variable. So if it is a random variable, then it will have some distribution already associated to it. Like we assume that our parameter is following this particular distribution, which we call it as a prior distribution. Okay, so we don't treat it as a constant. Rather, in Bayesian estimation, if we have some samples that are coming from a distribution x, and x has some parameter theta. So theta is the parameter here. Okay, and we are trying to estimate theta using the samples. May I request everybody to be on mute if you don't have any doubt. Yeah, Venkat Sai, yeah, thanks. So if you have any doubt, please raise your hand and I will call out your name. Then you can unmute and speak. Okay. So I might be covering the things in a quick fashion because we have to cover many things today within the given 2 hours of time. So if you have any doubt, please raise your hand. I will call out you. Thanks. Okay, yeah.
Sir, we are using here this Bayesian estimation to estimate this parameter. Yes, sir.
Yes.
Okay, sir.
Yes. Even this is also one method to estimate a parameter. Okay, so we will come up with an estimator that is best suited for this parameter. And the approach we follow is the Bayesian approach, which in some sense we use the Bayes rule. Okay, in between. So in Bayesian estimation, that's what I was saying. This theta is no longer an unknown constant. It will be treated as a random variable. random variable, and once it is a random variable, we assume a distribution to it. So theta, for theta we assume a distribution which is called as prior distribution. Okay, and in most of the cases you see that if theta is representing a probability, we in most of the cases we usually assume that theta is uniform between 0 to 1. So this is the most commonly observed case in practical scenarios also. Instead of giving some distribution to it, we will just treat theta is uniform between 0 1. Okay, so yeah, we have a prior distribution to us. Then we will sort of use Bayes rule, which is in some sense we know this Bayes rule, right? P A given B can be written as P B given A times P of A
Divide by P of B, sir.
P of B, right? So here also A B is replaced by the samples and parameter. So the same thing written in a different fashion. So observe, you can correlate this with the following equation also. So we are trying to estimate theta being equals to some big theta. Let me say this is a random variable. Taking the value small theta, given the samples, okay. So this can be written as what is the probability that this sequence of samples that occur if this big theta takes value theta times the PDF of theta. Okay, divided by probability of this samples, occurrence of the samples. Okay, so if you don't want to write x1 x2 xn, so it represents, in some sense this represents x1 is taking some small x1, x2 is taking some small x, so like this xn is taking small xn. So this whole thing in lectures, if you have observed, this is represented as one sampling. So instead of writing all like this, you can write simple S. S, that means you have observed n samples. After observing the n samples, we are trying to predict the value, good value for theta. So that is theta. You are trying to, in some sense, you are trying to find the probability that this theta takes this small theta value given the samples. It can be written as what is the probability of occurrence of this sample, this particular sampling, this x1, small x1, small x2, small xn, this S, given that theta has taken this value times the distribution, prior distribution of theta, which is, if it is discrete, it will be PMF. If it is continuous, usually it will be continuous, it is PDF, divided by the probability of occurrence of this sample, P of S. Okay, so now you can simplify this and see it in a greater look. So this particular thing can be written like this, given the samples is equals to probability of occurrence of the samples given the theta to be small theta into f theta of theta whole divided by probability of occurrence of the samples. Now we know few things. So this is the prior distribution. And when you do maximum likelihood also, you would have observed this is the likelihood, the probability of occurrence of this samples given theta is the likelihood, and this is the posterior. And this is just the normalization constant, which is independent of theta. So this is just a constant that is multiplied. So if I remove that constant, I can write that posterior distribution. If I ignore this constant, I can write this will be directly proportional to likelihood times prime. So this is what we do. What we do is we assume a prior distribution to the parameter and we observe the samples. After observing the samples, we can form the likelihood function. Once after forming the likelihood function, you take the product of likelihood to the prior distribution, and your posterior distribution will be directly proportional to this. If you want to equate, then you have to multiply this likelihood times prior to 1 by probability of the occurrence of the samples. But usually we just want the distribution. The constant doesn't play much role. So if we can identify which distribution, that is sufficient. So we update. So we assume something, you observe the samples. After observing the samples, you update the distribution of the theta. The updated distribution is called posterior distribution. The assumed, before observing the samples, you assume some distribution, right? That is called as prior distribution. And this is the connection between posterior and prior. Okay.
Sir,
So yeah.
Yes, if we ignore the constant, then the posterior mean which we will find, will that be accurate?
It will be accurate. See, usually posterior means of any distribution will not depend on the constant. Will be dependent on the parameters only. So you take any distribution, binomial or Bernoulli or Poisson, any distribution you pick, the expected value of that distribution will always be dependent on the parameter only. Okay, so that will not create any issue. It just multiplies a constant to it. It won't change the distribution too much.
Okay, but multiplying a constant to each of the sample means expectation will also be multiplied by that many times.
Okay, you are okay. See, the thing is, you understand the distribution, right? If you draw the PDF of the distribution, if you just multiply a scalar to the distribution, what will happen is it will just enlarge or compress, right? See, if you have the PDF like this, if you multiply some scalar to this PDF, the shape won't change. The shape will remain as it is, but it may be like this or it may be like this. Okay, either it will compress or it will enlarge if you multiply a scalar. If you add a scalar, then it will shift. But multiplying, it will multiply throughout the
distribution will not be changed, sir. But I thought that expectation can change, isn't it?
Expectation may change the value, but if you okay, see, the thing is okay, I understood your point.
So here we have the P of S in the denominator. So it will either multiply or divide depending on the value of P of S. So what you said that it will enlarge the distribution or it will compress. I think that is the correct. If it is addition of the constant, then it will move along the y-axis, either to the left or the right.
Right. Okay. Yeah, correct. You can think of in this way. Who asked this question?
Sir, I said
Prashant
Prashant. See, the thing is, any distribution can be centralized, right?
yes, sir.
Right?
Yes.
So all these testings, everything, whatever we do, estimation or testing, we somehow centralize the random variable first. Okay. So once you centralize the random variable, then multiplying with a scalar doesn't change the expected value, because expected value will always remain 0. Okay.
Okay.
Then you go back and see, what you do is you centralize it, and you understand the distribution. Then you take this distribution back to the same place. Okay. It will not change much. Okay. It won't matter much. So you will understand the distribution without the constant only. Okay.
Okay, sir.
So okay. So the key takeaway from this is this: the posterior distribution will be proportional to the product of likelihood with the prior. Okay. Let's see an example, and then we can move to week 11. Okay, one example is sufficient to discuss here. So let me write down the example for you. Okay, maybe 2 examples. Let's take. First example, I will take it very easily. Let's say x1 to xn follows IID Bernoulli P, and let's assume a prior distribution to P. So in order to come up with the Bayesian estimator, we need the prior distribution to be given to us. So let's say prior distribution is beta 11. Prior distribution for P is beta 11. Okay. Now what we have to find is find the posterior distribution of P. Okay. So this we know. We need also samples, right? With the let's say along with the prior distribution, the samples are observed to be x1 is x1, x2 is x2, and so on. Xn is xn. But what we know from the Bernoulli distribution, this small x1, small x2, small xn can either be 0 or 1. So there will be number of zeros and number of ones. Out of n random samples, we know that there will be some k zeros and n minus k ones, right? So that we can use, and this we can write down directly, I guess, because this is just a basic example. Let me write down. See, this is the prior distribution for P, which is beta 11. What is beta 11? By now you should know what is beta 11. So beta 11 is simply
X power alpha beta sum.
What are alpha and betas here?
1.
1. Beta is 1.
1.
So
Alpha is 1 and beta is 1.
Beta is 1. When alpha is 1, beta is 1, how will the distribution look? Okay, what is the PDF of beta distribution? It is directly proportional to
x alpha raised to minus 1 and 1 minus x beta minus 1.
When alpha and beta are 1, 1, what happens to this?
It becomes 1 into 1.
Uniform.
1 into
X raised to 0 and x 1 minus x raised to 0.
The uniform
So it will be 1.
Correct. So what do we mean by PDF is directly proportional to 1?
Uniform 0, 1, sir.
Correct. So beta 11, even though if we give it as a beta 11, beta 11 is nothing but uniform 0.
Here again, sir, if there is some constant, then it will not be uniform 0, 1. if there is some constant multiplied to 1.
Constant multiplied to 1?
Because it is not equal to 1. It is just proportional to 1.
Right, it is proportional to 1, right? Again, if you multiply anything, it will be a constant, right? PDF taking some value, and you know what is the constant is tau.
So
So you
any
know this,
constant
right?
C, if it is
It will not be any constant C. See, if you have understood the beta distribution, it will be tau alpha times tau beta divided by tau alpha beta or alpha plus beta, right? When alpha and beta are 1 1, everything it cancelled out and it will also become 1. Okay. So that's what I said. The constant will not play much role. That will anyway be cancelled out and it will become whatever we are assuming. Okay.
Okay, sir.
So you don't have to worry about the constant too much. Okay. That liberty we have. Okay. We don't have to worry about the constants.
Right, sir.
I don't know why too many people from outside IIT Madras are willing to join. Are these stats 2 students? Suddenly, why the count got increased to 54?
सर एग्जाम आ रहे क्योंकि
Even Sunday one is also revision session. Na? Okay, but anyway, I am admitting everyone. So it's fine. Okay. So that is why you don't worry much about the constant part. Okay. So the constant part will be managed. Yeah. So beta 1 1. If you see beta 1 1, do not worry. It's simply uniform 0 1. Now we have uniform 0 1 with us as the prior distribution. If it is uniform 0 1, what will be the PDF? How will the PDF look?
It is flat from 0 to 1.
Flat
1.
and it's just 1, right?
Yes.
So FP of P will be simply, this big P of P will be simply 1. Right? So prior is 1. Therefore, posterior density, if prior is 1, just go back. Okay. If prior is 1, so this way, if this is 1, our posterior distribution will be directly proportional to simply to the likelihood. So now I have to write the likelihood. So what will be the likelihood function? It is just the product of the densities of xi of small xi, where I is running from 1 to n. Again, you see all these are coming from Bernoulli P, right? So if x1 is 0, then here fx1 of x1 would be 1 minus p, right? If small x1 is 0, then the first term in the product would be 1 minus p. If small x1 is 1, then the first product would have been p. So if I have some k zeros and n minus k ones, then I will have in this product, I will have k 1 minus p's and n minus k p's. So therefore this product will become where k is the number of
ones, number of zeros,
or if you want to write in the other way, k is the number of ones in n samples. Okay, so this is k, and then I can write this product as like this. Now posterior will be directly proportional to the likelihood. The likelihood is this 1 minus p whole power n minus k, p power k, and times prior is simply 1. Now what we have posterior is something like p times p power k times 1 minus p whole power n minus k. So how does this look?
Beta
This
distribution.
looks like beta. And how can we compute alpha and beta for this beta distribution?
Alpha will be k plus 1.
Just try to write the powers as something minus 1 in both the powers. So this is how we can write p power. It has k, so but I need minus 1. So if I add minus 1 here, I should also add plus 1. So k plus 1 minus 1 will give me k. Similarly, 1 minus p whole power n minus k plus 1 minus 1. Now you can easily observe that this is alpha and this is beta. So alpha is k plus 1, beta is n minus k plus 1. So the posterior is directly proportional to p power k plus 1 and p power k times 1 minus p whole power n minus k, which in turn looks like the distribution of beta. So the posterior is beta k plus 1 comma n minus k plus 1. So now the posterior density or posterior distribution is beta this. If I know this posterior is beta this, then I can compute the posterior mean or the expected value of this beta distribution. So the posterior mean or the expected value of beta alpha comma beta would be alpha by alpha plus 1. Right? Posterior mean would be alpha by alpha plus beta, alpha plus beta. Here alpha is k plus 1 by alpha again is k plus 1 plus beta is n minus k plus 1. So here this k and this k will get cancelled out. Ultimately, we will be left with k plus 1 by n plus 2. Okay. So in problems, what we will ask is, we will give you the prior distribution. You have observed in week level assignments also. We will give you the prior distribution. We will give you the samples. So here I have taken x1, x2 to xn. But in questions, we will give you what small x1 is, what small x2 is, what small xn is also. Then in that, you know how many zeros are there and how many ones are there. So that means you know the value of k and also you know the value of n. Once you know both, you substitute here and you can compute the posterior mean as well as the posterior density also. So you can compute how the posterior density is, whether it is beta 12 comma 30 or 10 comma 12 or whatever. But depending upon the values of k and n, you can compute the posterior density as well as posterior. Okay. So that is one problem. Yeah.
Sir, we have to just remind the
Sir, in this
distribution
is
no, sir. We have to just remind our formula. Na? Formula is
no. Beta distribution will be given to you as in the formula sheet. Okay. So beta distributions PDF will be given to you. So you just have to map. Yeah.
So the beta, this posterior density, how do we calculate? Yeah.
From this expression. So we know
it will have to be proportional to that only, no?
So we know that beta PDF,
because those tau beta alpha plus beta upon tau alpha and tau beta, that will be 1, no?
That will not be 1. That will be
beta is equal to 1. Okay.
See, that's what constant you ignore. Okay, you don't worry about constants in writing or in Bayesian estimation. You don't worry about the constant.
Okay.
You just worry about for which distribution
we don't have to calculate the tau, no?
No.
We don't have to calculate
no.
Okay.
So So here we are
Thank you,
not
sir.
calculating taus or anything, right? Here you have to identify what is alpha and what is beta. Once you have identified what is alpha and what is beta, then you can directly write the posterior density is beta alpha, which is k plus 1 in this case, and beta is n minus k plus 1 in this case. So beta k plus 1 comma n minus k plus 1 will be the posterior density, because I know that the PDF of beta will be proportional to x power some alpha minus 1 times 1 minus x power beta minus 1. So here x is p and alpha is k plus 1 and beta is n minus k plus 1. So this and this has the same form, right? So that's how you connect posterior density also follows beta, since both the PDFs are proportional to each other. Okay, so constants you can ignore and simply you need the proportionality, whether this posterior is proportional to this beta's PDF or not. That's it. And I can tell you, if the samples are coming from Bernoulli or binomial, then the posterior will be beta. Okay, if the samples are coming from exponential distribution, then the posterior will be gamma. Okay, so that's how you can, if you want to remember, you can remember it in that way.
If Bernoulli, then it will be
Beta.
Sir,
Bernoulli and binomial, in both the cases, whatever the prior distribution you assume, the posterior distribution will be
beta.
Okay,
If
so let us do,
exponential,
then it will be gamma. Let us do one explicit example by taking the values.
Sir?
Yeah.
Sir, what if both prior and x both belong to normal?
Then we have some other fancy expression, right? If
Okay, sir.
prior is normal and if we have the likelihood also product of some e power something, then the posterior mean have some big fancy expression.
Sir,
That is also given in the formula sheet.
Okay, sir.
Okay.
Sir,
Yeah.
in the previous question, if we have to find the posterior mode, then how can we find that using the density?
Posterior mode, you don't worry, but posterior mode is basically that requires given 2-3 values, only then you can come up with the mode, right? So I don't think you need posterior mode.
Sir,
Here.
if here prior instead of beta uniform is given, how will you calculate the posterior mean for that?
This is uniform case only, right?
But the formula you have given, you have used alpha by alpha plus beta posterior mean. In that case, how it will be replaced if it is uniform?
It will not, posterior will not be uniform, right?
No, posterior mean of beta distribution is alpha by alpha plus beta, right, sir? In case of uniform distribution, how would it look?
How would it look? I didn't get that. What do you mean by how would it look?
Instead of beta 1 comma 1,
Hmm.
in the question, if it is mentioned, if the prior is uniform 0 to 1, what formula you will use, sir, here for
See,
calculating?
both beta 11 and uniform 01 have the same PDF, which is this.
Okay.
So even though if I give you beta 11, your prior PDF will be 1. Even if you have given uniform 01, you know what is the PDF of uniform 01, right? It's just 1. It will be just 1.
Yes, sir.
So there is no difference.
Instead of beta 1 1, if they have given beta 2 comma 1,
if they have given beta 2 comma 1, then the prior, what do you know about prior? FPP would be proportional to if it is
p to the power alpha minus 1 into 1 minus p to the power beta minus 1.
Beta minus 1, where you said alpha is 2, right? Then it will be 2 minus 1, 1 minus p whole power 1 minus 1. Then it would somewhat look like p power 1, p. It will be directly proportional to p. Then it would be here, instead of multiplying 1, you will multiply p. Then it, instead of p power k, you will get p power k plus 1. Then if you have k plus 1, then alpha would be k plus 2. Therefore, then the posterior distribution will be beta k plus 2 comma n minus k plus 1. Instead of this k plus 1, you will be seeing k plus 2 in that case.
Got it, sir.
Okay.
Thank
so
you,
that is
sir.
what we are going to do here. Now, in this case, I took an explicit example. Let's say I have drawn 5 samples from IID binomial 10 comma p. We are trying to estimate p, okay, and using Bayesian estimator. Let's say p has prior distribution is beta 2 comma 5. Okay, and now it's not 1 1, it's beta 2. Prior distribution is beta 2 comma 5. Okay, and now it's not 1 1, it's beta 2 comma 5. And let the samples also given to us. Let's say x1 is 8, x2 is 4, x3 is 6, x4 is 3, and x5 is 7. Okay, so I have given you the 5 samples also now. Our goal or the question is to find the posterior distribution and posterior mean. Okay, so we have to compute both. For that, see, for computing posterior distribution, what I know posterior is directly proportional to likelihood times prior, right? So in order to get the posterior distribution, I need the likelihood and the prior. Now prior comes from here. So prior is given to be beta 25. So if it is beta 25, just write down the PDF of this beta 25. How will the PDF will be proportional to, ignore the constants. You just need the proportionality. PDF will be proportional to p power 2 minus 1 times 1 minus p power 5 minus 1. Because it is beta 2 comma 5, I know that PDF will be proportional to p power alpha minus 1 times 1 minus p power beta minus 1. Here beta, alpha and beta are 2 comma 5. So this is, if I simplify this will be simply p times 1 minus p whole power 4. So just bring that p times 1 minus p whole power 4 here. So prior will be p times 1 minus p whole power 4. Okay. Now we are yet to find the likelihood. Now what will be the likelihood? So likelihood is basically what is the probability, or what is the probability that this particular sequence of samples occur. So what is the probability that the first sample shows me 8, second sample shows me 4, third sample shows me 6, fourth sample shows me 3, and fifth sample shows me 7. And all these samples are coming from binomial 10 comma p. So if it is coming from binomial 10 comma p, I know the probability of the first sample taking value 8 would be simply 10c8 times p power 8 times 1 minus p whole square, right? The first sample taking value 8 has probability this 10c8 times p power 8 times 1 minus p whole square. Like this, since it is likelihood, I have to take the product of all the probabilities. Next is x2, the second sample taking value 4. What is the probability that the second sample takes value 4? That is 10c4 times p power 4 1 minus p whole power 6, right? So like this I have to consider product of all the 5. So the first 2 is this, and this will be multiplied to 10c6 p power 6 1 minus p whole power 4, and this will be multiplied to the fourth sample is 3, so 10c3 into p power 3 1 minus p whole power 7. This will be multiplied to 10c7 p power 7 1 minus p whole power 3. So this is the likelihood. Agreed?
Yes, sir.
And here also you can ignore the constants. You don't worry about the constants. So there are many constants sitting here. This, 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 and this. So you can simply ignore the constants because you just need the proportionality symbol. You just ignore the scalars that are being multiplied. So this will be proportional to, I have p power 8 here, then p power 4, p power 6, p power 3, and p power 7. So if I add all, if I do the product, the powers will be added. I will get p power 28 times 1 minus p whole power, again 2, 6, 4, 7, 3, 22. Correct? Yeah. So this will be 22. So likelihood will be proportional to p power 28 times 1 minus p whole power 22. Then there is prior p times 1 minus p whole power 4. Now this will be proportional to p power 29 times 1 minus p whole power 26. Right, we were reduced to this form. Now we have to identify what is alpha and what is beta. Can anybody quickly say what will be alpha and what will be beta?
Alpha is 30, beta will be 27.
Right. So write this like this: p power 30 minus 1, 1 minus p whole power 27 minus 1. So therefore you get your alpha and beta. So alpha is 30, beta is 27. Now you can write down the posterior distribution. What is the posterior distribution?
Posterior mean or distribution?
Posterior distribution. It will be beta.
Beta 30, 27.
So this is the posterior distribution. Then you can find the posterior mean.
30 by 57.
Right. Posterior mean p hat or whatever is alpha by alpha plus beta, which is 30 by 57. So 30 by 57, you can use calculators and enter the value. Okay. So this is how you solve the problem related to Bayesian estimation.
Excuse me, sir.
Yeah.
Sir, can in this type of question it can be asked that how to find the posterior mode?
That's what I said, right? We will not be asking you posterior mode. See, if it is posterior mode, you have to use, you have to again maximize over thetas, and you have to come up with the arg of maximum of theta, which is a bit complicated. Okay.
Okay, sir.
So that's about week 10. Let me stop sharing this slide, and I will present the new slide. Yeah, this PDF will be uploaded in the live session notes. Okay. Let me share the new. Yes. I hope the new screen is visible to everyone. Weeks 11 and 12, hypothesis testing. Right? Yeah. Okay. So far we have done week 10. Now we will do week 11 and 12 collectively, because both are from the same concept, which is hypothesis testing. So we will see again what is hypothesis, and then we will talk about acceptance set, and we will try to spend more time on size and power of a test by solving more problems on it. And then I will talk about p-value, and at the end I will just mention some standard tests we have, and I will also give you which tests you have to give more importance and which tests you can ignore for now. Okay, since we have only 4-5 days, you have to revise from week 1 to 12, so you will not be getting too much time also. So that is why I will give you some most important tests you should definitely focus on, and if time permits, we will also solve 1 or 2 problems related to the tests. Okay, so let's start. Again, let's start with the definition of hypothesis. Hypothesis is basically a statement that is being proposed, or you can define that as an assumption that is based on some known facts, but it hasn't been proven yet. Okay, so it's just basically a statement that is said for the sake of argument, and we will try to verify that statement. So few practical, or in general, you observe some sort of hypothesis in real life is these are the examples. If I replace battery of my vehicle, then it gives better mileage. So this is an assumption, right? You don't know, but you assume that if I replace my battery, because of the past observations, if you replace old battery with new battery, definitely the performance will be better. And the next thing is if I eat more, then I'll gain weight. If I study for 8 hours a day, then I can score good marks. So these are all assumptions or statements without logical or mathematical proof for it, right? And all these are kind of hypotheses. And the textbook example which we have seen so far is if I have so it's like there are 2 types of coins that you can see in the real life. One may be unbiased coin and another may be biased coin. So I have given you a coin which can be unbiased or biased, and how can we predict whether the coin is unbiased or biased, right? So this is also comes under hypothesis testing, where we assume that the coin is unbiased. We treat that as an hypothesis, and we try to verify that hypothesis, and in verifying, in the process, we try to toss the coin more and more times, and then we will decide based on the outcomes we observe. We will decide whether to accept that it is an unbiased coin or whether to reject and say that it's a biased coin. Okay, so this is a standard textbook example which you see in every textbooks or in any of the video lectures where you come across hypothesis testing. This is a standard example. Okay, so what we do in hypothesis testing is we actually use the samples and decide between a null hypothesis and alternative hypothesis. We have 2 hypotheses with us. This is called as binary hypothesis testing, and in our course we only have binary hypothesis testing, where we have 2 hypotheses. One is called null and another one is called alternative, and based on the samples, based on the observed samples, we decide whether to accept null or reject null. Okay, for example, just before the textbook example we discussed, right, you can put your null as the probability of getting head is 0.5, which is nothing but saying the coin is an unbiased coin. And you can put alternative hypothesis as something like probability of head is other than 0.5, which may be 0.6 here. It's just an example. So if the probability of getting head is 0.6, then this is a biased coin. This is biased towards head, right? So based on this is what we do. Using the samples, we decide whether to accept the null or to reject the null. rejecting null in some sense, we are accepting the alternative. Okay. And in order to perform this hypothesis, yes.
Sorry, probability of head is equal to 0.6. This can also be null statement, means null hypothesis.
Yeah, this can also be null statement. Can also be. See, that is possible.
In example, you have written, is it standard or what?
No, this is not standard. This is just an example. Okay, you can define your null as probability of head being 0.2 also.
Okay, sir.
Okay, yeah. Okay, so yeah, the next thing is, in order to perform this hypothesis testing, we need to define an acceptance set. So I hope most of you have gone through the lectures, and by now you should know what is the importance of acceptance set in the hypothesis testing. So that will give us the test. So let me explain what is this acceptance set again. We have the samples, x1 to xn are samples coming from the distribution x, and we also define our null hypothesis and alternative hypothesis. And if you have a distribution, that distribution has a sample space, right? That x can come from a sample space, which is chi, defined here as chi. So chi is just the sample space of x. If x is belonging to chi, then this particular, we call n tuple or vector n, it's like n samples come from chi power n, right? So because all x1, x2, xn's are IIDs of x, so x1 comes from the sample space chi, x2 comes from the sample space chi, x3 also comes from chi, and xn, and so on, xn also comes from chi. So this n tuple, this ordered n tuple, will come from n dimensional chi cross chi cross. So this chi power n is nothing but chi cross chi cross chi and so on n. Okay. So if the samples will belongs to chi power n. Now the definition of acceptance set is any subset you consider from this chi power n will be an acceptance set, is an acceptance set. So that's how an acceptance set is defined. So you consider any subset of all the possible from the set chi power n, that will be an acceptance set. And then we define an equivalent test. So if you have an acceptance set, an equivalent test is defined like this. If the observed samples small x1, small x2 and so on, small xn belongs to A, then you accept H0, else you reject H0. Okay. So understand this. Let me take a solid example about this. Let us suppose we toss a coin 4 times. Okay. Suppose we toss a coin 4 times. Okay. Now, if it tossed 4 times, there are 4 outcomes which can be represented with 4 random variables x1, x2, x3, x4, and all these are IID Bernoulli P. Why Bernoulli? Because I'm tossing a coin and the outcome will be only binary, either it will be head or tail. So if the outcome is binary, then it will follow Bernoulli distribution. And this P we don't know. We are testing for that P. Someone has said that P is 0.5. That will sit as the null. So P is 0.5 is null, and alternative is P is 0.6. Now we have tossed the coin 4 times, right? So Bernoulli distribution has sample space either 0 or 1 or head or tail. So you can treat it in any way. In this particular example, chi is simply 0, 1, where 0 represents tail and 1 may represent head. If chi is this, I have 4 samples with me. So the ordered tuple x1, x4 will belongs to chi power 4. Now, how will the chi power 4 look? What elements that chi power 4 will have? Either all zeros, so 0, 0, 0, 0, or 3 zeros, 1, or 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and so on like this. All the 4 length sequences which contains zeros and ones, right? And so on, 1, 1, 1, 1. So chi power 4 will contain these many elements. Can anybody tell me how many elements?
2 to the power of 4.
2 to the power of 4, which is 16. So the cardinality of this is 2 to the power 4, which is 16. So out of 16 elements, this chi power 4 has, any subset you consider. So the acceptance set is a subset of chi power 4. That's it. So in some sense, what we do is, out of all these possible outcomes, we define for few outcomes, we accept the null, and for few outcomes, we reject the null. And if you form a set which contains all the outcomes for which you accept the null, it forms an acceptance set. Okay. So maybe I will just write what I said. Just a second. Okay. So if I toss the coin 4 times, this chi power 4 will contain all the possible outcomes. Right? Chi power 4 will contain all the possible outcomes. Correct. Among this, all the possible outcomes, for some outcomes, we accept the null, and for the other, we reject the null. Okay. So we just split out all the possible outcomes, we just split it into 2 separate sets, which will have the outcomes for which we accept the null, and the other set will contain the outcomes which we reject the null. Now, the set of all the outcomes for which we accept the null is called the acceptance set. Okay, and for defining the acceptance set, it's in our hand. So you can consider, you can split this all the possible outcomes set into any possible 2 sets. So you can just consider first set contains only this element and every other element contains in the other set. So you just have to break this big set into 2 small sets, and this breaking is in our hand, right? So we have to decide which outcomes, for which outcomes we will accept the null and for which outcomes we reject the null. And the set of all outcomes for which we accept the null is called the acceptance set. That's it. And the other set is called rejection set. Okay. And why we require this acceptance set is we define the test accordingly. So once we have the acceptance set, once we form the acceptance set, for each acceptance set, we have an equivalent test. Okay. And among this, our goal is to find the best acceptance set, in some sense the best test. So there are many possible acceptance sets for this particular problem itself. Can anybody guess how many subsets are possible for this chi power 4?
16 subsets.
16. Chi power 4 itself has
2
16
raised to the
elements.
power
16.
So this cardinality of A would be 2 power 16, which is way large. It's much bigger. So among all the different possible acceptance set, we have to come up with the best acceptance set. Yes.
Sir, what is the value of that chi to power? What is the meaning of that chi power 4 equals to 2 to the power 4? That
this is just the cardinality of chi power. So how many elements are there in this chi power 4?
Sir, I just was confused that why is this value of A is greater than this chi 4? Because that is 16, this is 2 to the power 16, so why is that?
See, this has 16 elements, okay? See, if a set has some 5 elements, how many subsets are possible from that particular set? Do you know this? So if some set has n elements, 1, 2, n, then number of subsets of S.
2 to the power n, sir.
2 to the power n, right? So the same thing here also we are doing. So the chi, see, it's not not cardinality of A. The number of possible subsets.
Oh, okay, sir.
For chi power 4 is 2 power 16. Okay, and since acceptance set is any subset, so there are, for acceptance set, there are 2 power 16 possibilities.
Yes, sir.
Okay, so okay, that's how, maybe it's my bad. So okay, so this is how you should interpret. Okay, so among 2 power 16 possible acceptance set, that means we have 2 power 16 tests. Among these 2 power 16 tests, we have to identify which test is better among all the possible 2 power 16 tests. For that, we use two metrics that are associated to every test, and based on the two metrics, we kind of conclude which test is better and which test is not so good. So those two metrics are size and power of a test. Okay, based on this size and power, we decide whether the given test is good or bad. Okay, so let me formally go through the definitions of size and power of a test, and you will we can then directly jump into the problems. Okay, so size is also called as significance level. It is denoted as alpha. It is the probability of the type 1 error. What is type 1 error?
The probability of rejecting H0 when H0 is true.
So here we have two hypotheses, which is null hypothesis and alternative hypothesis. And in reality, if null is true, but you perform the test and you end up concluding that null is false, in some sense, you end up rejecting null. So that's an error. In reality, it is true, but you ended up guessing it to be false.
Sir, one second. Here, null is true means it is in the acceptance test, acceptance set, right,
no,
sir?
It is not in the acceptance set. I will explain you with an coin toss example only. See,
okay, sir.
If the coin is fair coin, in reality, you don't know whether the coin is fair or unfair. But in reality, the coin has only two ways, possibilities, right? Either it would be fair or unfair. I have given you a fair coin. That means which is the probability of getting head is 0.5. Right? If I have given you a fair coin, the null is true actually, which is not known, but actually it is true. But you have performed the experiment, that means you toss the coin more and more times, but after 100 tosses So you ended up getting some 80 heads and 20 tails. Even though it is a fair coin, there is a possibility that you might get 80 heads and there is a probability of getting 80 heads and 20 tails, right? And that is the only sampling you observe. And after observing, what will you decide is, since I got 80 heads, this is definitely an unfair coin, or it's a biased coin, right? Which is an error. I have given you a fair coin, but you ended up guessing it to be an unfair coin, which is an error, right?
Yes, sir.
So that is what it is. So in reality and your prediction. So if your prediction matches to reality, then there is no error. But if your prediction doesn't match with the reality, then that is an error. Agreed?
Yes, sir.
So type 1 error is, after performing the test, you ended up rejecting H0, given null is true. Okay, so this is type 1 error. You reject H0 when null is true.
Sir, here it is assumed that null means true, alternate means false, means counterfeit coin, something like that, sir.
Unfair coin.
So, but here we are taking into consideration the acceptance set or not. Here, when we are doing the tossing of the coin, we will have an acceptance set and still reject H0.
See, when will you reject H0 based on the acceptance set only, right? If your outcomes false in the acceptance set, then you accept the null, or else you reject the null, right? Okay. See the test. You observe the samples. After observing the samples, if it falls in the acceptance set, then you accept the null, or else you reject the null, right? If your null is stating that it's a fair coin, what would be the best acceptance set you consider? All the your acceptance set will contain equal number of heads and equal number of tails, right? That's how you generate your acceptance set, right? But if you had got some 80 heads and 20 tails, then that will not be in your acceptance set and you will definitely reject the null. Even though it's a fair coin, you end up guessing it to be an unfair coin. So that's the, maybe I will write it. What this error is basically, given a fair coin to you, we end up guessing it to be unfair. And this is an error. This is an error because given a fair coin, that means if you treat the probability of getting head is 0.5, that means null is true. In reality, null is true. But you perform the experiment after a series of tosses, after observing the samples. If your samples doesn't belongs to the acceptance set, you will definitely reject it and you conclude that it's an unfair coin, which will lead to an error. That kind of error is called the type 1 error, where you reject the null when null is actually true. And the size is basically the probability of type 1 error. This is probability of rejecting the null given the null is true. Okay. And this is an error. So main thing you should observe that this size of a test is an error, probability of an error. And similarly, power of a test is 1 minus beta, where beta is probability of type 2 error. Again, type 2 error is the other type. So it can also happen that given an unfair coin, after performing the experiment, you end up guessing it to be a fair coin. So that means the alternative is true and you perform the experiment and you see the samples, after seeing the samples, it might end up such that your samples might belongs to the acceptance region, and what will you do is we conclude that we accept the null. So that is type 2 error. So we accept null when alternative, in reality alternative is true here. For the example, given a biased coin, we end up guessing it to be an unbiased. Okay, so you can now understand the difference between type 1 and type 2, I guess. You always think about this example. So you have null to be fair coin or unbiased coin, alternative to be biased coin. So there can be two possibilities of errors. One is given a fair coin to you, you end up guessing it to be an unfair coin. The other error would be given an unfair coin to you, you end up guessing it to be a fair coin. So both are different kinds of errors. And alpha is probability of type 1 error, beta is probability of type 2 error. And this is probability that you accept the null given alternative is true. Okay, so this is beta. And you can rewrite this power. Now power is 1 minus beta. Directly you can write power as probability that you reject null given alternative is true. Right? So how powerful is your test? So with how much confidence you can reject the null when alternative is true. That's the power. Okay, and this can be used at total law, total law
Sir,
of
that is
probability. And
power of 1 minus beta. Yeah, it is power is same as 1 minus beta.
yes, power is 1 minus beta. 1 minus beta is power. So how powerful is your test, and how significant is your test in some sense, or in some sense the size of the test. This is the size of the test. And if you observe, this alpha and beta are the probabilities of errors, and we usually want our errors to be very low, and this probability of occurrence of this errors to be also low. So what we try to get is, for a good acceptance set, we try to keep alpha and beta as low as possible, because alpha and beta are in some sense errors, probabilities of errors, and we want the probability of error to be very less, right? Therefore, for a good acceptance set, we try to keep alpha and beta as low as possible. Okay, let me just quickly recall what all we discussed so far, and this is called as Neyman-Pearson paradigm of hypothesis testing. So what all we do in this hypothesis testing, we have the samples coming from a distribution, we define a null, and we define an alternative, and we also define a test, and this test is defined by an acceptance set. Once you have an acceptance set with you, then we can define the test, and test is, if samples fall in the acceptance set, you accept the null, otherwise you reject the null, right? And for getting a best test or best acceptance set, we kind of use two metrics, which are two errors. Okay, two metrics which are significance level and power of a test. Significance level is alpha and power of a test is 1 minus beta. Alpha is probability of type 1 error and beta is probability of type 2 error, where these two errors are, type 1 error is rejecting null when null is true, and type 2 error is accept null when alternative is true. Okay, So based on these two metrics, we decide which acceptance set is good, which in turn tells us that which test is good. Okay, so that is what we do, and this is called this is what we do in hypothesis testing. Okay, so have a flowchart of this.
Pearson paradigm.
That's the name of this
This
sequence.
complete
Sequence, yeah. Okay. Okay, now let's do problems. Okay, let's try to find alphas and betas for different sets of problems. And yeah, I forgot to mention about test statistic. Test statistic is a statistical inference for the samples. Okay, so once you observe the samples, you define a test statistic which is function of the samples, which will be helpful for us to decide whether to accept or reject. Okay, so it is just a statistical measure. Okay,
is it the mean, sir?
It will not be mean always, but if you are trying to test for mean, then the test statistic would be sample mean, but it is not always guaranteed that it should be mean. You can also take sum. Test statistic may also be just the sum of samples. So that test statistic will define.
It is also defined by observer only.
Observer only.
Will that be given, or we should only assume it, sir?
No. Will that it will be given to you. Okay.
So, as acceptance test is defined by observer, in the same way, this test statistics will also be defined by observer. But what is the base of these things?
What base is, see, the thing is, you have the samples with you, but how do you use the samples? You can't use individually, right? You have to come up with a statistical measure, one statistical measure or some value of the samples, which can represent the samples, right? So for that, this test statistic is used.
Okay.
Okay.
I mean, one question here on this test statistics. In the graded assignment or practice assignment or something, somewhere options were given like where the test statistics is probability or a variant. I mean, sorry, some mean or something like that. Okay. I mean, I think this corresponds to the mean, right? Average.
This corresponds to sample mean.
Sample mean, yeah. So do we have example of how that other would look like? I mean, when we say test statistics corresponds to probability.
Proportion, I mean. You mean?
Okay. Yeah. I don't remember the exact option, but yeah, there was something.
It will be proportion. Even the proportion also takes the same form. See, proportion is also like out of all the samples, how many samples has taken that particular value, right? The number of samples that has taken that particular value divided by total number of samples. In some sense, instead of x1 plus x2 plus and so on x100, you will have the number of samples that are taking a particular value.
Okay, got it.
Okay, it's just the proportion you consider.
Okay, yeah, got it. Yeah, thank you.
Okay, yeah. So yeah, so this test statistic is in some sense is just a mathematical inference for the samples, and it will be a function of the samples. Usually if you are trying to test for mean, the test statistic will be sample mean, because the sample mean is the best comparable to the population mean. Comparable statistic, best comparable statistic value for the population mean, right? So therefore, if you are testing for mean, then you have to use your test statistic. Best test statistic would be sample mean. You can use sum also, but that will not be the best. Okay, so do not worry much about this test statistic. We will provide you the test statistic. Okay, and The next thing is that is why I have given you all these things. In this example, whatever you see, all will be given, and the question comes at the down. So test statistic is sample mean, and the test is also given to us, which is you reject H naught if this test statistic is greater than C, and this C is called the critical value. Okay, so this is called critical value, this T is called test statistic, and after observing the samples, you can compute the test statistic, because after you observe the samples, you can substitute those values and get the test statistic value. And if alpha is given, then you can compute the critical value, and then you compare the value of T and the value of C. If T is greater than C, then you reject null. If T is less than C, then you accept. That's how you
Will
perform.
It always be greater, sir?
No. See, that is also, again, this is just an example. Test can be like reject H naught if T is less than T also. Okay. Now, given all these informations with us, find alpha and beta in terms of C and Fz. Fz is the CDF of standard normal. Okay, so let us try to compute standard normal. So standard normal, I mean 0, 1, normal 0. Okay, so we have the test statistic with us, we have the test with us, we have to compute alpha. For computing alpha, just write the definition first. What is alpha? Alpha is probability of reject null given null is true, right? The next step is, when do you reject null? You reject null if T is greater than C. So that means if T is greater than C, given null is true. So what is null? Null is P is equals to 0.4. Okay, so small p is being equals to 0.4. This is alpha. Now T is a random variable because T is a function of samples, and samples are random variables, so T is a random variable, but we don't know the distribution of T, but we can use CLT to convert this T, or to approximate this T to standard normal. What should I do to convert capital T to the standard normal Z?
Sir, we can subtract by its mean and divide by standard deviation.
Right. So T to Z. So what should I do? I have to subtract expected value of T and divide by standard deviation of T. Will this work? Is this true?
Yes, sir.
Yes.
Yes.
Yes. So that is what we are going to use now. For that, we need expected value of T and standard deviation of T. T is the sample mean. What will be the expected value of T? So T is x1 plus and so on, x100 by 100. All these things you should write directly. So this is just the sample mean, x bar. What is the expected value of x bar?
X bar itself.
X bar.
Mu. Distribution.
Distribution mean. So what is the distribution mean? So this will be expected value of x bar will be mu. And what is mu? What is the mean of Bernoulli P?
P 0.4.
P. Right? And what is the standard deviation?
P 1 minus P.
So okay, compute variance. Variance would be variance of x bar, and this would be Forgot everything. Sigma square by n.
Yes.
Is this correct? What is sigma square? What is the variance of population mean? What is the variance of Bernoulli distribution with
P multiplied by 1 minus
P multiplied by 1 minus
P times 1 minus P divided by n. Now this is variance, but I don't want variance, I need standard deviation. So what will be the standard deviation?
Root P 1
Square
minus
root of
pi.
P into 1 minus P whole divided by n. Right? Here n is 100. So instead of n, we can write 100. This will be 100. So we will do the same thing. We have the standard deviation now. We have P for expected value and we have the standard deviation. We will just bring and substitute here. Now alpha will be probability that T minus expected value of T whole divided by standard deviation of T greater than whatever I do on the left hand side, I should do on the right hand side. C minus expected value
SD of T.
SD of T given P is 0.4.
Yeah.
Okay. Now the left hand side, I don't need to worry. So this will all just be Z, right? So probability that Z being greater than the small c minus expected value of T is P, but it is given that P is 0.4. So I can write 0.4 whole divided by standard deviation of T is square root P into 1 minus P by 100. But it is given that P is 0.4, then the standard deviation would become simply 0.4, 0.6 whole divided by 100. Yes. Okay. So from here, probability that Z greater than C minus 0.4 into 10, because square root of 100 will be 10 and that 10 comes to the numerator, and in the denominator I will have square root 0.24. Right. So I can further simplify this probability that Z greater than C minus 4, 10C minus 4 whole divided by square root 0.24. Okay, till now it's okay. How will I bring CDF of Z?
1 minus 10C minus
so
4.
this I can write it as 1 minus probability that Z is less than or equals to 10C minus 4 by square root 0.24. Right. Now this I know it is fz of whatever the right hand side values. So this will be 1 minus fz of 10C minus 4 by square root 0.24. So this is alpha. Okay. So given C, given some fz value to you, corresponding fz value to you, we can compute alpha. Now you see this expression, alpha and this critical value C are dependent on each other. So you give me C, I can give you alpha, corresponding alpha. You give me alpha, I can find corresponding value of C. Right? If I want C, what should I do? Given alpha, I will do alpha minus 1 minus alpha and fz. Okay, let me write. So alpha is this. Now if I want to find C in terms of alpha and fz inverse. So what will I do? I will just simply bring this fz of whole thing to the left hand side, alpha to the right hand side, then take fz inverse. If I do all that thing, I will be remained with 10C minus 4 divided by square root 0.24 will be equal to fz inverse of 1 minus alpha. Right. From here, I can write C is equals to 4 plus square root 0.24 into fz inverse 1 minus alpha whole divided by 10. So you just do the calculations. You just have to multiply square root 0.24 and then bring 4 to the right hand side. Then divided by 10, you will get C to be this. So you see both C and alpha. So what I want you to observe is, observe that both C and alpha are interconnected. If you know one value, you can compute the other value. If both are not known, you cannot compute either of them, right? So in problems, if it is given that the value of alpha, then you should know how you can find the critical value for that corresponding alpha. Whereas if critical value is given to you, then using critical value and fz, you can compute alpha. Okay, so if you change alpha, the C value will change. If you change C, the alpha value will change. Okay, so I hope everybody is convinced about how alpha and C are interlinked.
Yes, sir. Sir, fz inverse can we calculate when it is fz of C is given, and we can calculate fz inverse of C?
So small values or very standard values you can remember, but you don't worry, we will give you. If fz inverse is required, we will give you.
Okay, sir.
Okay. So this is how we find alpha. We can also find beta in the same way in terms of C and fz, where do the same approach, right? What is beta? Let me do that here in the next problem. But you try for the above this particular problem, you write what beta is. Beta is basically probability that you accept null given alternative is true. So if alternative is true, now you should take P to be equal to 0.4, or what should I take?
0.6.
0.6. Here I have taken 0.4 because null is true. If alternative is true, instead of P is equals to 0.4, it will be P is equals to 0.6. And when do you accept null? You reject null if T is greater than C. When do you accept null?
When T less than equal to C?
Correct. So if you are rejecting null when T is greater than C, then you accept null when T is less than or equals to C. That's the counterpart, right? So beta would be, I will just write what beta is, then you can compute from there. Okay, where shall I write? I will write here. Okay, alpha is this, but beta we know, probability that you accept null given alternative is true, right? So accept null means when T is less than or equals to C, we accept null. So what is the probability that T being less than or equals to C, given the null alternative is true, alternative says P is 0.6. Okay, now everything is same. So you don't know the distribution of T, therefore we know the distribution of T, but computing probabilities we don't know because we don't know the CDF of T. So therefore we try to convert T to the standard normal and compute the probabilities. So you subtract expected value of T divided by standard deviation of T on left hand side and right hand side. Now when you substitute, here we have substituted 0.4, right? Instead of 0.4, now P value would be 0.6, and this would be same. This would be 0.6 times 0.4. The standard deviation will be same, but the expected value of T would change to 0.6. Okay, everything else is same. Now here in this particular case, you don't need to do 1 minus of probability. You can directly write this as fz of something. Okay, so do I have to compute and write and show?
No, sir, we can do.
You can solve this. Okay, so let's move to another example. Now I have increased my number of samples. Instead of 100, I have increased it to 500. Instead of Bernoulli, I have come up with all the samples that I am drawing from normal mu comma 1. Okay, one is just the variance. Mu is the one we don't know. We are testing for mu. Null is defined as mu is equals to +1. Alternative is mu is equals to -1. Again, test statistic is sample mean. Sample mean, I mean, this is just x1 plus and so on, x500 whole divided by 500. Okay. And test is also given to us. You reject null if t is greater than c. Again, we have to find alpha, beta in terms of c and fz. The same problem, instead of Bernoulli and p's as the parameters, here we are drawing samples from normal distribution and our parameter is we are testing for mu. Okay, so let me compute.
HA alternative, it is everything except null, or it can be defined in
everything.
Means null statement, null hypothesis, and alternative hypothesis. Is it contrary to each other? No?
Of course, yes, right. If it is same, then what are we trying to?
No, contrary. I mean, everything except null hypothesis is alternative hypothesis, isn't it?
Everything except null hypothesis. Sorry, I'm not able to.
Means here you have written mu is +1, and HA. Sorry.
Alternative. This is alternative.
Alternative is mu is -1. So I mean, HA should be everything other than +1.
It may not be. I can define my alternative. I can test against something else, right? So you are saying that mu should be not equals to +1.
Yes, sir.
So that is one alternative. Even alternative is also an hypothesis.
In the above question, you have used this thing that alternative hypothesis is.
I used alternative as p is equals to 0.6, right?
Okay, I misunderstood somewhere.
Okay. See, the thing is, p not equals to 0.4 also I can keep. I can define my hypothesis also in that way. But I can also define my alternative hypothesis in this way also. There is no long in defining my alternative like this. Okay. Okay. Yeah.
Sir, there was a question in activity 11.2. I had a doubt in that question. So instead of solving this question, sir, can you solve that one?
Okay.
It's regarding this alpha and beta only. It's
just a second, then let me open the portal. Okay, those who want to solve, just try to solve this problem also. Meanwhile, I will just open that activity 11.2.
Yes, sir. Question number 3.
Okay, consider one sample from this and let null and alternative hypothesis be this and this. Consider a test that rejects null if mod x minus 200 is greater than 40. So they want alpha. Okay. Okay, we can do this.
Okay, sir.
Okay, then is this okay to do, or do I have to write the steps and show in this particular problem, question 2? So it is same as question 1. The only change is instead of Bernoulli, here the distribution is normal. There instead of testing for P, we are testing for mu. Okay.
Sir, I have got a query here. Sir, this alternate hypothesis, we are taking mu as -1. And we are rejecting HO if P is more than C, right?
Okay. Maybe.
So,
yeah, you are correct. That is not an proper way of defining the test.
Yeah. So, okay. Now it is okay.
Now it is okay, right? Yeah.
Now it is okay. Okay. Sir, these kind of things may be asked in exam, like say mu is -1, and I can have alternative hypothesis like mu not equal to -1, maybe less than -1 or more than -1. It can be anything, right?
Yeah.
So in whatever questions come, it will be very clear there to conclude that what will be the alternate hypothesis, because there can be ambiguities also. Like I'll think some way, somebody else may think some other way also.
So the thing is, usually how you should think about the alternative will also be given to you. We will mention whether you should perform right tail, left tail, or two tail.
Right.
Okay. So that will also be mentioned.
Right, sir. Okay.
So in this case, when we are calculating alpha, P is not given here. So P we have to find according to the normal
What is P here? There is no P here.
No, P means the probability. Like Bernoulli P we are given as 0.4 and
here mu is alternate null. For null, mu is given as -1, right? See, just write the definition. What is alpha probability that you reject null given null is true? What is null is true? What does null say? What is null saying?
Mu equals minus.
Null is -1.
Mu is -1. So this is mu is -1. And when do you reject H0? When T is greater than C?
T is greater than C. Yes.
That's it. Alpha is probability that T greater than C given mu is -1. That's it. Now, since you don't know the CDF of T, you try to convert this T to standard norm. Okay.
Yeah, sir, one thing, if had you not mentioned this reject H0 if T is more than C, suppose you have not mentioned this. Now, what should I consider as my alternative hypothesis? Not equal to 1, right? It should be double-tailed.
Not equals
not
to
equal
-1.
to -1, sorry. Not equal to -1,
if
right?
we haven't given any alternative hypothesis and test also, then you should think of how you should define alternative and test.
Like here, it is very clear that reject H0 if T is more than C. If it was not mentioned, like this line was not there, suppose, then if somebody asks me what should be my alternative hypothesis, it should be like mu not equal to -1, right?
You reject H0 if
X bar minus mu mod should be more than C, like that it will come.
Like that, yeah.
But it should be both ways, right, sir? I mean, both plus side and minus side we have to consider for this.
Okay, I don't think that is not the proper way of defining, but that's not what we wanted to discuss here. Okay, so I just wanted to put that discussion out because you will not be in that particular case during the exam.
Okay, that kind of thing will not be there, right?
No. We will not leave you to define test by your own.
Okay, thank you.
So so forget about that part, but see, that is why I have given till here. So this is the information given to us, and even in the previous example also I have given information till here, and then I have asked that find alpha and beta in terms of C and epsilon.
So this is some.
Okay, now it's like T is just the sample mean. You can compute expected value of T as well as variance of T. From there you can compute the standard deviation of T. Okay, so everything can be computed, and just do T minus expected value of T divided by standard deviation of T.
So when we have given this normal mu comma 1, standard deviation will be 1, no?
Standard deviation will be 1. Standard deviation will not be 1. This is sample mean, right? This is population standard deviation, which population variance, which is sigma square. But when you compute variance of x bar, it would be sigma square by n, right?
Sigma square by n.
Okay, the challenge is to compute expected value of t and variance of t. Okay, or since I have given the t is nothing but a sample mean. This we studied in week 7, 8, right? Given a samples, given a distribution to you, given samples, and consider the sample mean, what will be the expected value of the sample mean? It will be population mean, right? Which will be mu. And variance of the sample mean also is computed, and it will be sigma square by n. And sigma square here is 1, and n is 500, so it will be 1 by 500. Therefore, standard deviation of x bar would be 1 by square root 500. Okay, so this is 1 by square root 500, and expected value of x bar would be mu. But for computing alpha, it is given that mu is minus 1. So therefore, expected value of x bar would be minus 1. So you have to subtract minus 1 and divide it by 1 by square root 500. And the left hand side will start following standard normal. And the right hand side you will have is c plus 1 by square root 500. And then write it in terms of fz. 1 minus of, you take 1 minus of, and then write the other term which is left as fz. And that's it. You will get alpha in terms of c and fz. Okay. So this problem, I hope this can also be left as an exercise and you can work it out. Let me take that problem from AQ 11.2.
Sir, can you show once again the first example, sir?
These slides I will upload, don't worry. Okay.
No, given condition, have you considered in the calculation of probability?
That we considered, no? We will consider. Only then you will compute expected value and variances. Here I have taken p is equals to 0.4. Only then this expected value of t became 0.4, or else it would have been any other value. Okay, I have considered.
We have not used conditional.
Can we know what are the values of alpha and beta in the question which you have asked us to solve?
This one?
Yes.
I didn't ask the final value. I just asked alpha and beta in terms of C. Okay.
Okay.
So this will be C plus 1 by square root 500 greater than C plus 1 by square root 500. Okay. So alpha would be, I'm writing it directly the answer, 1 minus fz of C plus 1 by so this is multiplied by 10 and we will have root 5 also. Okay. So this will be 10 root 5 C plus 10 root 5. This is what alpha is. Okay, try solving and you will get the same answer. Okay, let me quickly do this and I have to discuss p-value also. See, it is given that a one sample has been drawn from binomial 400 comma p, and null is given to be p is equals to 0.5 and alternative is given to be p not equals to 0.5. Okay, and consider a test. That rejects.
So today the session will extend beyond 8.
Looks like, because I have to discuss one important topic which is p-value.
Okay, sir. Thank you, sir.
if mod x minus 200 greater than 40. Okay, so this is the test given to us, and we are asked to find alpha. So alpha is again probability of you reject null given null is true. So what is null is true? Null is true is 0.5, and you have to find the probability that mod x minus 200 greater than 40 given p is 0.5. Now this mod x minus 200 greater than 40, I can write it as, if I remove the mods, I will be getting minus 40, sorry, x minus 200 is less than or equals to minus 40, less than minus 40, or x minus 200 greater than 40 given p is 0.5. So this is what it is, right? If I remove mod, the inside x minus 200, if it is greater than 40, then also the modulus will be greater than 40, or the inside x minus 200, if it is less than minus 40, even then if I take modulus, then x minus 200, modulus of x minus 200 will be greater than 40. Now this will be probability that x being less than, so this particular thing will become x less than 160 or x greater than 240 given p is 0.5. Now you have to compute the probability where this x is coming from binomial 400 comma p, right? So what is the probability? So since it is OR, I can write it as probability that x less than 160 given p 0.5 plus probability that x greater than 240 given p is 0.5. Okay, and we know x follows given p is 0.5 in both the cases. Now here x will follow binomial, x will follow binomial 400 comma half. Since p is 0.5, since null is true, I know that x follows binomial 400 comma half. Therefore I can find these probabilities, right? So this is nothing but probability that x takes 0 plus probability that x takes 1 plus, and so on till probability that x takes 159. And this is the next part is probability that x takes 241 plus, and so on it goes till x takes 400. Okay, so I can compute each of the probabilities. Since I know x is binomial, I can compute all these probabilities, and finally you will get something like summations. I is equals to 0 to 1, 400 ci half power 400 plus, again I is equals to some, this is still 159, and then I starts from 241 to 400 ci half power 400. Okay, is this okay?
Yes, sir.
So that is alpha.
Sir, one thing, using the conditional probability formula will also give the same result. That probability of A given B is joint probability of A and B multiplied by B.
Then how will you find the probability that P being 0.5?
Okay.
No, right?
Sir, here in this we are not converting into normal and all, right, sir?
No need, right? We directly know, we can directly compute the probabilities, right? Why we convert to normal, standard normal, is because in order to find approximate probabilities, because standard, only for standard normal we know the PDF values, right?
Okay.
So that's why we convert to standard normal and compute, approximate the probabilities. But here, since you can compute the probabilities directly, there is no need to convert to standard normal and do Okay.
Okay, sir.
Okay, so maybe I will just spend some 15 minutes, not more than 15 minutes on this p-value. And once if you have understood p-value, I think you are almost ready to attack the final exam. Okay. So even p-value is not so difficult in some sense, but if you have better understanding about the PDF and the connection between the test statistic and the critical value, also the connection between significance level with the critical value. So previously I mentioned, understand the connection between alpha and C, right? So if you change critical value, your significance level value will change. Alpha and C are that connected. And on the graph also, you should be able to interpret for a particular C, what is my alpha? So what is the alpha represent? Okay, if you can able to have that visual interpretation with you, then p-value is very, very easy for you. Okay, maybe I will give you that interpretation. I will try to give you that interpretation within the next 10 minutes. So p-value.
Sir, you will also cover that right-tailed jet test and left-tailed jet test.
See, all tests follow the same approach, right? Try to understand. I might give you which tests you should be more focusing on for your final exam. Okay, I may not be able to discuss all the things because it will kill a lot of time, but I will give you which tests you should focus. And I don't think once if I have given you the most important tests, all the tests will follow the same approach, right?
Okay.
Just go back and watch the lectures or go back and watch the week 12 live sessions. That is sufficient. Okay. Okay. So let me talk about p-value for the next 10 minutes. So p-value, it is defined as the lowest significance level alpha for which the null is rejected for the test statistic is equals to t, where the small t is the value that comes from the sample. Okay, so this is the actual definition, but I don't want to talk in regards to definition itself. Rather, I just wanted to connect p-value with significance level, and you might think that this t is somewhere which is not related to critical value, but that is not true. As I mentioned, alpha is connected to the critical value, right? This you have to keep this in mind. Critical value C, right? So if I change the critical value, my alpha will change. And if I equate critical value to this small t, that means if write it in a different color. So if critical value C is taken to be the test statistic value. So the test statistic value, I mean, after observing the sample outcomes, you compute the test statistic, and that is equal to C. Then for that critical value, the corresponding alpha you find, I say alpha star, is p-value. Okay, so you see the connection between the test statistic, critical value, and alpha and p-value. So alpha, this p-value is one special case of alpha, one special value of alpha. When this will, so what is that special value is when this critical value takes the test statistic value, then its corresponding alpha will be the p-value. Okay, and now let me give you the connection between the critical value and alpha. So far we are just simply saying that critical value is connected to alpha, alpha is connected to critical value. If I change critical value, alpha will change. and if I change alpha, critical value will change. But on the graph, let's say this is the PDF we have. Okay, on the graph, let's say this is X. Okay, this is not X, this is the test statistic.
Excuse me, sir. So in this graph, this is the PDF of the samples, right?
This is the PDF of the distribution.
Okay.
Okay. So this particular PDF, can you guess what x-axis represents?
Normal distribution.
What x-axis? X-axis.
Density. X-axis, sorry, value of random variables. X.
Okay. So this is X and this is Fx. Okay. Now Now, where do you think the critical values lie? Is it x-axis or y-axis?
Y.
C. Critical value.
It will be on x-axis.
Because, see, if you remember, we define tests like this, right? Test as you reject a null if my random variable takes more than C. Right? So our, let's say X is coming from normal mu comma 1, where we are testing for mu. Okay. And null is something like mu is again -1, alternative is +1, something like this, and you reject null if this X takes value greater than C. So here you are comparing X with C, so that means C will lie on x-axis, somewhere on the x-axis. Okay, if I say C is this, I say C is this. For this corresponding critical value, what would you think alpha would be? So on the graph itself, which one is alpha? So this is C. Okay, let me give you a hint. Alpha will be a region.
It's fx of x greater than C.
Value after C will be rejected.
Okay. Okay. So do you think that this is the region
No,
of
this
alpha?
question.
Below the function.
This is the region of alpha, or this is the region of alpha? Or...
No, it will be this.
It will be
the area under the curve.
area
On
under
the right side.
curve and on the right side, right?
On the right side.
So,
sir, why left side is not considered, sir? Since it's a
see
normal
the test.
distribution.
See the test. So you
X
reject
is
null
greater than C.
if X is greater than C,
Okay,
and
got
your
it.
rejection
C.
and if your rejection
Region.
region is on the right side.
Okay, sir. Got it, sir.
Okay.
Yeah.
And yeah, just a second, let me erase this. Now, if you are convinced that now, okay, this is region. What is alpha actually? Is it just the region, or alpha is a value, right? What is the connection between alpha and this region?
Sir, alpha, it's a probability of the curve under the until x-axis portion of it, no, sir?
Okay, so it's basically the area under this particular curve after C. So whatever the area, so this region has some area, right? So area of orange region is alpha. Okay. So you know the whole area under this curve would be equal to 1, right? And the probability that your test statistic value, even the test statistic will also be on x-axis only. Test statistic will be somewhere here or somewhere here. That will depend on the samples. Once after looking at the samples and this critical value, you compare t with c. If t or this x, whatever the value this x takes, x can be here, here or wherever. After observing only, we know where x lies. X can take any value from minus infinite to plus infinite. But you reject null if your x falls greater than c. That means, what is the probability that your x falls after c, or your x falls right side of c? Only then x will be greater than c. So that particular probability is basically the area under this particular curve, right? From here. Right? So this is basically probability that x greater than c, given mu is -1 or whatever. But what is the probability that x being greater than c? It's area under this curve. Yes or no? How would you compute the probabilities if density curve is given to you? You integrate, right? This probability is basically fx of x dx.
So here you are taking one x only. There will be x1, x2, x3.
1x or x1, x2, x3, and then you take the test statistic. Everything represents a value, right?
Yes.
PDF is of complete sampling, or just one random variable.
See, even if it is sample, test statistic is a random variable, right?
Yes, sir.
If I consider test statistic, then that particular test statistic will have a distribution.
Yes, sir.
And it will have a PDF.
Yes, sir.
So x is a test statistic.
Here x is just, since I have considered only one x, one sample, x itself will be the test statistic for me. If I had considered x1, x2, xn, then test statistic would also be a function of x1 to xn, which will again be a random variable. It just simply becomes a random variable, right? Instead of x, I would have used t. Here it would be t. Here it would be ft of t. Right? Instead of this, I would have another random variable. That's it. But the whole idea is this: even if you consider t or x, if you want to compute the probability that x being greater than c, from the density function you have, what will you do to the density function to get the probability? You integrate from c to
1,
c to infinite, or c to infinite, right? That's what probability, right? And that probability is nothing but alpha, right?
Yes.
So basically, the area under the curve represents the significance level. So if you have this interpretation in your mind, then it will be easier for you to understand p-value in a better sense. So now see that. So I'll take the new graph. I have this example, but okay, I will write it here. So now, okay, before I move, I want everyone to convince yourself that for a particular critical value, if I have this test like this, for example, I have this greater than c on, then for a particular c, whatever the area under the curve to the right of c will be equal to the significance level. Is this okay to understand, or still people have any doubts in this?
What did you say?
So the critical value, for a critical value c,
yes, sir,
alpha will be the area under the curve to the right of C.
Yes, sir.
Okay. There is no doubt about this.
No.
Now, for
sir, here we have considered that conditional part means alpha is what it is when the null is true. So
see when null is true, mu is -1. When mu is -1, x follows normal -1 comma 1.
Okay.
So when x follows normal -1 comma 1, it has some PDF, right? It will have some PDF. So the peak will be at -1. So this may not be the graph. Maybe this is -1. This might be -1, and the standard deviation is also 1. Okay, so this will have a PDF.
Understood.
And once you have the PDF, once you have the critical value, after the critical value, whatever the area under that particular curve, that will be equal to the significance level. Okay.
Yes.
So for a critical value, if I change critical value to the left or right, correspondingly my alpha will change, right? That is also there, right? So again, so let's say
area will be changed.
So let's say I have this curve with me. I have this curve with me. Again, I have x on the x-axis, fx of x. It doesn't matter if it is t or x. You can take t also. T will also be a random variable. That's it. Okay. Some small t, not t. This will be this. Now, let's say I consider C1, one critical value C1, another critical value C2, another critical value C3, and there comes, after observing the sample, there comes the small t. Okay, that will also be on this x-axis, and you can consider C5, C4, C5, like this. So for different critical values, accordingly you will have alphas, because the area to the right of these will be different for each of the critical values. Right. For the first one, it would be the area under the curve to the right of C1, which has larger area. So this will have value of alpha to be more, right? This area under the curve is more. So if I say this is alpha 1, C1, correspondingly it will have some alpha 1. Alpha is very large. Alpha 1 is very large compared to C2. C2 is, for the when the critical value is C2, then its corresponding alpha value will be alpha 2. And if I have to compare alpha 1 and alpha 2, which one is bigger?
Alpha 1, sir.
Alpha 1. Now similarly, for C3 there will be corresponding alpha 3, and for this particular t, there will be some alpha, which we call it as a p value. So let me denote it as alpha star. For C4, again for C4, it will have some alpha 4, and for C5, this will have some alpha 5. So if I change critical value, you treat like I started from C1, I will have some alpha 1, and I move to C2, then my alpha will reduce, right? My significance value is reduced. If I move to C3, my alpha 3 is further reduced, and if I move to T, it is reduced. C4, alpha 4, if I move to C4, C5, if I move to the right of right on the x-axis, my alpha is getting lower and lower. Okay, so is this okay?
Sir, so you mean to say that in that alpha condition we give no probability of t greater than c, t less than c. If you say that t is equal to c, then it is a p value, right?
T is equals to t,
C,
not
C.
T is equals to c.
Is a p value then.
Right. Now this t is, right? This t
is the point between the rejection and exception.
Now that is where I am coming. So now you see this t lies in the blue region, right? Because this blue region is this. After C1, that's the blue region I call. So if that is the case, C1 is lesser than T, right? Does everybody agree with this? C1 is less than T.
So T is the
test statistic value. Test statistic value. T is the.
It was capital T. Why we have written in small?
Why we have written is, after observing the samples, you know the values, right? X1, X2, X3, small x1, small x2, small x3, and small xn. All the sample values you know, and you can compute the test statistic value, right? After observation, one particular sampling, you can compute the test statistic value.
Will be variable, means will be different for different samples.
Different samples. But we observe the samples, right? We observe one sampling, right?
Yes, okay.
Right?
For one sampling.
For one sampling, you consider one sampling, and for that particular sampling, you can compute the test statistic value, and which will be equal to some small t.
Yes.
Okay. C1, now C1 is less than D. Will everybody agree to this?
Yes, sir.
If C1 is less than T, which is this T is equals to T. If C1 is less than capital T, what should I do? Whether I should accept or reject? Okay. This blue region is a rejection. Accept.
Accept.
Okay. Our test is T greater than C. You reject null if T is greater than C. Okay. So our test is, you reject the null if T is greater than C. If C is C1, then will T be greater than C or less than C?
Less than C. Accept. We will accept.
No. Just look at the graph.
It will be greater than C.
C1 is here. T is here.
C1 is smaller than T.
C1 is smaller than T. So this T is greater than C1. This T, which is small t, is greater than C1.
Greater than C1.
Then what will we do? Will we reject or accept?
Reject.
From the graph also, if you see, for this particular C1, this is the rejection region. This whole blue is the rejection region. If your test statistic falls in the rejection region, then you reject, right?
In the upper example graph, sir, you showed the orange region was rejection region or it was acceptance?
This is rejection region. Okay. This is alpha, right? This is the rejection region.
Yeah. Okay.
This is the right side of this is a rejection region. So my point is here is, for C1, if your critical value is C1 and if your test statistic lies here, you will end up rejecting the null because your test statistic value is greater than C1. Similarly, if your critical value is C2, even then this T falls in the rejection region, correct? Yes, no? If your critical value
so only C4 and C5 will be the acceptance region.
Yes, sir.
So whatever critical value you consider to the left of this small t, you end up rejecting the null. True? If your critical value is left of this t, any critical value consider to the left of small t, you will reject the null.
Yes. For this particular example.
For this particular example only.
Yes.
And what is the least significance level at which you reject your test statistic?
That will be small t.
That will be small t, right? That is what the definition of p-value is. The lowest significance level, alpha, for which the null is rejected. After that, you will start accepting. Okay. That is the actual definition of p-value. So to the left of small t, you will accept, and your alphas are bigger, greater than this alpha star. So if your critical value is left of the small t, your corresponding alpha will be greater than alpha star. So here alpha 1, alpha 2, alpha 3 are greater than alpha star. Okay. And for alpha 1, alpha 2, alpha 3, you reject t. Even for alpha star also you reject. But after alpha star, you start accepting small t because it falls in the acceptance region. To the left of, if your critical value is C4 or C5, then the small t is lesser than C4, which we start accepting the null. So any critical value to the left of small t, we reject. Any critical value that is right of t, we start accepting. Okay. There is a change of conclusion at this particular point t, and at this particular point t, the corresponding alpha you compute will be the p-value, and that alpha is basically the lowest significance level, the lowest alpha for which you reject the null. Any alpha that is less than this alpha star, you accept. You understood? So any alpha being greater than p-value, you reject the null. Okay, any alpha. From the graph you can see alpha 1, alpha 2, alpha 3 are greater than alpha star. For the alpha 1, alpha 2, alpha 3, the corresponding critical values are this, and these critical values are lower than this t. Therefore, you end up rejecting. Whereas any alpha that is less than, any alpha greater than or equals to p-value, you reject. Any alpha less than p-value, you accept. Okay. The connection between alpha significance level and the p-value. By just comparing alpha and p-value, you can conclude whether to accept or reject. Just like you compare t and c, test statistic value and critical value, you can also compare significance level value and p-value. Okay.
Sir, one question. Here test can be defined as t less than c also.
That is also defined. Everything will be inverted.
Then, why it is in short note it is written that the lowest significance level alpha. In that case,
so the previous page, please. The previous page.
See, if you reject null, if t is less than c, then what happens is the graph will all look inverted. That's it. You just invert with respect to y-axis.
In that case, that will be highest significance level.
No. Even that also will be the lowest, because the left-hand side also, when you go left of x-axis, your alpha will reduce. So everything will be just inversion of y. I will just draw that if t is less than c, this is how it will look. Okay, so the test is you reject null if T is less than C. Okay, if this is the case, it may be like your C can be somewhere here. Okay, for this particular C, anything left of C you reject. So that means this will be the rejection region. Okay, if this is C1, then this will be alpha 1, corresponding alpha 1. Okay, again here also, if your test statistic falls here, even then you reject, right? You reject if the test statistic value is less than critical value. Here the test statistic value is less than critical value, you reject. For this alpha 1 you reject. If your C2 is, if your critical value is here, C2, for this critical value also you reject because your small t is less than C2. And this will be alpha 2. Even here also alpha 1 is greater than alpha 2. Okay. So this is, even for C2 also you will reject. The lowest critical value at which you stop rejecting is at T. So at this particular point, the corresponding alpha would be the P value. This would be the P value. And after this, again you start accepting. If you consider some other critical value, which is C3 or something, for this C3, if you compare C3 and small t is greater than C3. And eventually you will accept.
That's what I thought that this is the maximum at which we can accept. So this is the maximum alpha.
This is not maximum alpha, right? Alpha 1 is greater than alpha 2. Alpha 2 is greater than P value. Even at alpha 1 also you are rejecting.
Sir, we are alpha 2 we are rejecting.
We are rejecting, na? Alpha 2 is greater than P value.
Sir, the area left of the T we are rejecting. So any C3 or C4,
no, C3 we are accepting, no sir.
C3 we are accepting, right?
C3 we are not rejecting.
That's what. See, these are areas, okay? This won't go negative. Alphas won't go negative, right? And if you go, if you start from C1, your significance level will be the topmost, highest value. Alpha 1 is top. At that top value also you are rejecting. C2 also has some alpha 2. At that point also you are rejecting. Then you reduce alpha further. How do you reduce alpha? If you move left on the x-axis, your alpha will reduce, your significance level will reduce. So reduce the significance level till you reach this.
It reaches T, small t.
At this particular point also you will reject. After this point you start accepting. So this is the least alpha at which you reject. So if you further reduce your alpha, you will start accepting.
You have to accept.
So again it will be like the lowest possible value for alpha for which you reject.
Sir, is it lowest? So area is greater than
here. No. Here T is the lowest point at which you reject. In the previous one, it was the highest value at which you were rejecting.
No, I'm not talking about the this x-axis value. Alpha is the area, so area will be decreasing.
Alpha 2 is small.
Just a second.
Alpha 2 will be smaller than alpha 1.
Do you agree with area decreasing?
Yes, sir.
Area decreasing means significance level is decreasing.
Yes, sir.
So you start with a big alpha, there you reject. You try to reduce your alpha, reduce your alpha, reduce your alpha, and you come up to a point at which that is the least alpha. I mean you started with some 0.7, brother. 0.7, then you made 0.6, 0.5, 0.4, 0.3, 0.2. Then after 0.2, if you further reduce, if it happens to be that you are accepting the null, then 0.2 is the least alpha, right? You start for any alpha greater than 0.2, you reject. For any alpha less than 0.2, you accept. So what is the least alpha at which you are rejecting? Is 0.2, right?
So, sir, what question here? So, I mean, at some point when we start accepting it, I mean, is it possible that some value again it will start rejecting it?
No,
Because
no.
See,
No, after that, I don't think it will.
If I see the graph, right? So we have a C1. We are claiming that anything below C1, we are rejecting it. Then even T is below C1, right?
Then we reject, right? See, if critical value is C1 and the tested statistic value is T, small t is less than C1, and even the test says the same thing. If if T is less than C, you reject.
Correct.
So we reject.
Correct.
If your critical value is C1, you are going to reject. For C1, the significance level value is alpha.
Okay.
And even for C2 also, you will be rejecting because your test statistic value is less than C2.
Less than C2. Okay, got it.
You reject. And for C2 critical value, the corresponding alpha is significance level is alpha 2. Okay. At the significance level alpha 2 also, you are rejecting. You consider any critical value that is greater than T. Okay, any critical value. Let's say this is C4. Even you consider this also. Small t is smaller than C4, and you end up rejecting.
Right.
For this C4 also, it has some alpha, right? Maybe it is alpha 4. Okay. One thing we know that alpha 1 area is great. See, the area, that white region is more than green region and then orange region. That means alpha 1 is greater than alpha 2, alpha 2 is greater than alpha 4, and alpha 4 is greater than p value. Right?
Alpha star.
Which is alpha star. Okay. At alpha 1 significance level also we are rejecting. At alpha 2 also we are rejecting. At alpha 4 also we are rejecting. And any alpha that is greater than this p value, we will reject. Right?
Okay.
At p value also we will reject. But after p value, that means any alpha that is less than p value, you start accepting. So when can any alpha be less than p value? When the critical value is left of t.
Critical value is less than C.
Less than t.
Less than T, yeah.
Right. So if C3 is this, and if it is left of t, then only then for that critical value, the corresponding alpha 3 would be smaller than p value, because the area under the curve is further reduced. So p value will be greater than alpha 3. For the significance level alpha 3, we accept the null. Right?
Okay.
So on the number line, if I just plot alphas, if I just simply plot alphas, this is 0. There is some alpha 1. There is some alpha 2. There is some, sorry, alpha 1 is greater, right? So this is 0. So there is some alpha 1 and alpha 2. Then there is alpha 4. Then comes alpha star, which is p value. Then comes alpha 3. Okay. So for all these alphas, we are going to reject. So after this alpha, for any alpha, we are going to reject. For any alpha that is less than alpha star and between 0 to alpha star, you are going to accept. See, out of all these possible alphas, which one is the smallest alpha for which we are rejecting the null, which will be alpha star.
Okay, got it.
Okay. Prashant?
Yes, sir. Sir, understood.
Understood? So in both the cases, whether it is t less than c or t greater than c, or even though it is two-tailed, even for two-tailed also, p-value is simply the lowest significance level at which you start accepting the null, or the lowest significance level at which you will be able to reject the null. Okay. So for problem purposes, what you do is, in order to compute the p-value, if the problem is to compute p-value, what you do is, instead of this c, whatever the c you see here, you just replace this with small t. So you have to identify what small t is. So in this particular example, there are 100 samples drawn from IIT Bernoulli P, and null is given to be p is equals to 0.4, alternative is given to be p is equals to 0.6, and the test statistic is given to be just the sum of the samples. Observe, it is not divided by 100. It's just given that take t as sum of the samples. Then we have defined the test statistic to be, you reject the null if t is greater than c. Suppose, so this is also given to us. Suppose we observed 50 heads out of the 100 tosses. So this is one sampling. So we have performed the experiment and we have tossed the coin 100 times and we have observed that 50 heads has occurred. Then what would be the value of test statistic? So what is the value of t for this particular sampling?
50.
40. Heads is 40 and no, heads is 60 and
okay, I should also define. So x takes value 0 if tail and 1 if head. Okay, all xi's. Now what will be the test statistic value?
50.
There are 50 heads. Okay.
0.5.
Test statistic is just the sum of the samples. You have 50 heads and 50 tails. That means 50 of the xi's are ones and 50 of
so it will be 50.
Will be 50.
T will be 50.
Right. So this is 50. This 50 is this p, small t. Now what you have to do is, in order to compute p-value, just simply replace this small c with 50. So p-value is nothing but alpha star. You know the significance level is basically probability of rejecting H naught. Rejecting means t greater than c, given null is true. Null is true, that means small p is 0.4. But for p-value, instead of this c, the only change you do is you take 50, which is small t. Okay. So in some sense, we have given you the critical value and we are asking you to compute alpha. Okay. You have to identify what is the critical value given from the test statistic, from the observed samples. Okay. So from here, this you can rewrite in just terms of fz. Since c is known to us now, you will get alpha star to be something in terms of fz's, 1 minus fz of something. Okay. From the given information, you just substitute the fz value and get the p value. Okay.
Sir, could you please repeat this explanation for this problem once?
Okay. So for computing p-value, you have to identify and replace the c with this small t. So this small t is basically test statistic value of one sampling that you can get from the given information. Given that we have observed 50 heads out of 100 tosses. So that means one sampling is given to us, which is 50 heads and 50 tails. Therefore, the test statistic would be 50 ones. So if I sum up all 50 ones, I will get 50. So test statistic value for this observed samples would be 50, which is nothing but small t. Now, the only thing what we have to do is, instead of C, you just replace it with 50. And everything other is same. So the p-value is basically the significance level. So instead of p-value, you just write down the formula of significance level. And while you write down the formula for significance level, instead of C, you just write 50. And then just do the same.
That means basically whatever we get from the sample, that will consider as critical value, right?
That is considered as critical value.
And based on that, we'll calculate what is that alpha, where we'll reject it.
And that alpha is called as p-value.
Yeah. Okay. Thank you.
Okay. Yeah. Okay. So that is about p-value. And one final thing about this is, we have studied many standard tests in week 11. In week 11, we have studied z-test, and in week 12, we have studied t, chi-square, and f-test. Solve some problems related to z-t. Okay. And chi-square also, but mainly focus on this z-test and t-test, and also look at chi-square test. For the exam purposes, you can ignore f-test. Okay, to solve some problems related to chi-square and z-test and t-test. Okay, is this okay? I have given many hints for your final exam.
Chi-square, Z, T and chi-square you said, right, sir?
Yes. So 80% of the focus should be on Z and T test, and some 20% focus you can give out on chi-square test. Okay. So with this, I am almost done with my revision, and do focus on the topics which we have discussed in the last session as well as this session. If you just simply follow these two sessions along with mock, if you are able to solve mock problems, then you can score. I hope you can score around 65 to 75% of the paper. You can solve 65 to 75% of the paper. But if you want to score 100 out of 100 in the end term, you should also focus on other topics also. Okay, you should prepare from week
12 also. Week 12 also.
Week 12, as I mentioned, week 12 we will not be asking too many questions from week 12. Whatever the questions we ask also will be very basic, and here also I have given you some hints, not from week 12, but for the other weeks I am mentioning what all things we have discussed. If you just simply focus on that, then you will, I hope you will definitely able to score 65 to 75%. Okay. Yeah, that's it. All the very best for your final exam. Hopefully,
Thank you, sir.
I will meet you in future courses.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you so much, sir.
Thanks a lot for joining, and have a good day. It's been a long session, but I hope this will help you for your preparation for your end.
Yes, sure, sir. It was very well helpful.
It was very helpful, sir.
Okay.
Thank
Okay, I
you,
will
sir.
upload this PDF, both the PDFs, and you can access it on the portal. And the sessions are also available on YouTube. You can come back later. Okay, with that, we have come to the conclusion, end of the session, and thank you so much for joining, and all the very best for your exam. Bye.
Thank you, sir.
Thank you, sir.
Bye. Good night.